carbon dioxide emission, researcher and engineer have been seeking to provide a sustainable and environmentally friendly material for many reasons. They're available, they're renewable, they're low weight, they're non-toxic, and they're low cost. Among other natural fiber, flax fiber have been proved to be an excellent candidate to replace synthetic fiber like glass fiber due to many reasons. We can see in the table the specific strength and the specific modulus for the flax, they're equal or even higher than one for glass fiber. There also shows cost reduction and energy consumption about 100% less than glass fiber. Despite all these advantages, flax fiber are suffering from some limitation. They actually have variability in their mechanical properties based on where they plant, where the weather, the soil, and the harvesting. They're also incompatible with matrices because we're dealing with polar and non-polar material. They're also poor resistant to moisture due to high percentage of cellulose. They're also limited in their impact performance. My motivation in that study, since 1994, Canada has been the largest producer of the flax in the world, specifically for flax seed. So what they do, they extract the flax seed, leaving the flax plant wasted, and they call it like where the flax fiber comes from the stem of flax plant, and they call it flax straw, and they actually burn in the field. Also, because of the lack of confidence in the capability of the flax fiber and the relative deficiency of their data and their mechanical performance. Therefore, my objective is to comprehensively mechanical characterize the hybrid composites, also their water absorption behavior. I also investigate the impact performance of the hybrid composite and their low velocity or low energy between 5 to 40 joule. Also study the damage response of the hybrid composite as a function of stiffness degradation, permanent strain, and crack density. In a way or a method to kind of limitate or overcome the limitation of flax fiber, I hybridized the flax fiber with the low content of carbon fiber. As you see, 2 layers at each side, a hybrid or sandwich between 12 layers of a flax laminate. I manufactured the composite using a wet hand layup technique followed by compression molding. Compression molding technique was carried and was controlled by 3 main parameters: time, pressure, and temperature, in order to produce a composite with 4 millimeter and fiber matrix volume fraction of 50-50. Curing cycle took about heating up the composite up to 150 Celsius for under 2.5 bar, and then curing it for 2.5 hours under 150 Celsius, then cool it down to the room temperature at 5 bar, which is 0.5 megapascal. I manufactured 2 configurations. I'm going to name them in the presentation as type A and type B. Type A is where the flax are oriented in unidirectional. Type B, they're oriented in angle ply. I characterized, or I made a deep mechanical characterization on the hybrid composites. I did tension, compression, bending, torsion, and rockable hardness. Due to the limitation of the time, I'm only going to cover the bending. It's one of the important characteristics related to the sandwich structure. As we know, bending, it's a combination of 3 loads: compression, tension, and shear. The outer layers, which is the carbon fiber, handle the tension and compression, whether the core layers hold the shear stress. There is a theory behind having a thick, low weight of a core. It's because whenever we increase the thickness, we increase the momentum of inertia, and momentum of inertia, they're actually inversely proportional to the maximum stresses on the both carbon fibers. We see here that 2 results for type A and B. We can divide that into 3 regions. So we see like a elastic region where whenever we increase the force, the displacement increase up to a certain point where fractures start in the tension layer. Then the force will drop about 20 to 25%. You see that flax fiber as a core are able to hold the force for quite a bit time until the last or final failure, in which that crack propagated from the tensile side up to the compression side. We see here that the bending stiffness give us between 40 to 44 gigapascal, If we compare the modulus for bending to the other modulus that we got from different mechanical characterization, we find that bending is the highest, because that's actually the mechanism of doing sandwich structure, is to provide high rigidity to do the material with no weight added. The hybrid composite for type A shows or manifests better performance than type B. That's related because the flax were oriented in the unidirectional, aligned with the applied load, which provide high load capacity that restrain the crack initiation and propagation. I also perform morphological analysis to see the quality of bonding between fiber matrix or fiber to fiber. I've taken 20 to 25 images from different locations of each composite. And we see here that there's wall bonding, there's no sign of delamination or debonding. I also carried determined the volume fraction of each constituent. I used the imaging picture that I got from scanning electron microscope, and I processed that under Omnium image software. We see here the volume, fiber volume fraction is between 46 to 43%. The matrix from 52 to 54, and the porosity or the void is less than 3%. I also carried a water absorption test. So what I did is I prepared a specimen and immersed them in the water for up to 90 days. We see here type A and type B shows a rapid increase in the water for about 25 days, and then they kind of saturated, so we see like they will level off. I compare my result that I want to get it from the hybrid composite to the one available in the literature for pure flax. So in the literature, it was showing that pure flax in the unidirectional one absorbed about 17% of the water. I compared that to my type A showed 4.8%. Type B showed 8.3%. We see here that there is about 100 to 250 water reduction by using only 2 external layers of carbon fiber. I also performed a deep impact characterization on the hybrid composite using in-house pendulum impact tester. I performed the impact or characterize it based on their energy absorption, their damage evolution, the crack length, indentation depth, and impact strength. We see here the relation between the impact energy applied and the absorbed energy for both composite type A and B. We see here both of them show kind of a linear relation up to 30 joules. We also could notice something, that there is kind of overlapping between both composite type A and type B. We see that that's an indication that majority of the load or the mechanism were held by the carbon fiber, and minor was contributed by flax fiber, because we see like a little bit higher absorbed energy for type A. Type A shows the penetration energy is 37 joule. Type B shows a penetration energy of 40 joule. That was also compared to what's in literature for pure flax. We see 10 for unidirectional one, and for angle ply it is actually 25 joule. We see here close-up pictures of the penetration that happened in the penetration level. So we see type A and type B. We have to consider that when the impactor is hit the composite, the front face that facing the impactor, it's experienced compression load. So we see like the fiber were buckled. And the back face, we see a tension. The surface experienced a tension where it shows some damage like delamination, fiber rupture, and fiber pullout. We also could notice that for unidirectional, we see the cut is more like a vertical cut, whether for type B we see more an X shape. We also can notice that type A created a bigger damage area than type B. We also determined the impact strength for the hybrid composite based on their energy absorbed, based on the crack length and the thickness of the composite. We see here the impact strength right there is between 380 and 500 kilojoule per meter square. That was also compared to the one for pure flax. So you see like the difference is about more than 500%. When introducing a new material, it's very important to study the damage evolution, so how the material is react with the presence of damage. Based on the damage model, classical model, they define damage as a surface density of physical discontinuum. So the damage, which is the D value parameter, were actually determined based on the loosening or the reduction of their modulus. So what we did, we take each specimen and then we load it and unload them for 5 to 7 level of stress based on their ultimate stress. Each cyclic load, we measure the deterioration in the modulus. We know when the composite or any material experience load and unload, they tend to have different damage mechanisms such as delamination, interfacial failure, interlaminate failure, and those are permanent strain which cause actually a deterioration in the modulus. We see here the damage evolution for type A. For example, for tension, we see that damage were slow up until the inflection point where it starts to increase rapidly and then they level off. We also try to compare what were the hybrid composite that we have with actually an existing pure flax. So here from the literature, we see kind of the profile that we got, the sigmoidal profile. It's similarly the same. That's only like for us to give us an indication that most of the damage was attributed by the flax fiber itself. You see under compression, it had a threshold, then it increased for quite good down, then it started to plateau. For pure flax, the one available in literature, that was, you see, obviously the damage were less comparing to that one. This is attributed more to the reorientation of the microfibrils in the flax fiber. We also study the permanent strain, accumulation of permanent strain for tension and compression for type A. We see here a quadratic profile. Pure flax shows also a quadratic profile where the damage accumulation were between 0.083 to 0.085%. I also study the damage evolution of permanent strain to type A. It's only, we could have had like available data in literature to kind of relate that, but we see here that the damage for tension is about 10%, however compression it shows about 20%. And still the permanent strain shows a quadratic profile. We also study the crack evolution, so actually what happening in the damage evolution. So we want to really kind of relate between the profile to the actual damage happening in the material. What we did is monotonically loaded the specimen at 20%, 60%, and 80%. We see here on your right the compression, on the left the tension. So at 20%, we see there is initiation of a crack at the interfacial of the fiber bundle. At 60%, we see they become more obvious, so most of the cracks are within the bundle, so intra-bundle cracks and interfacial cracks. At 80%, we see that the cracks start to enlarge, so they become and they propagate it, and mostly the dominant is the intra-bundle cracks and the interfacial cracks. We see here in the compression, it shows like a different damage. We see most of the bundle are more accumulated, but that's because they buckle, and that's what we kind of experience. We also wanted to see what is the role of the carbon fiber within this crack. You see here, when there is initiation of a crack and propagation, the carbon fiber, which is the bottom one, it works as hinder and prevent the crack from going and propagate along this material. We also try to put them as values and compare them between the pure flax. So we see here hybrid composite shows me about 10% of the damage. Flax shows me about 20% over here. For compression, the damage about 20% for both hybrid composites, and the flax shows about 40% of the damage. We see here the reduction between around 100% reduction in the damage. In conclusion, I performed a deep mechanical characterization on my hybrid composite, including the water absorption, and that was performed in one published paper. I also examined the impact performance of the hybrid composites at low velocity between 5 to 40 joule, and that was presented in another published paper. I also studied the damage evolution of the material based on their accumulation of damage, accumulation of permanent strain, and crack density. The paper is still under revision. In the future work, I would like to quantify the behavior of the composite under fatigue load. I also would like to perform a microfinite element analysis to explore the influence of different fiber orientation. I'll probably add the 0 and plus minus 45 and see the effect of that. Also, we noticed that most of the damage actually occurring within the fiber bundle, flax fiber bundle. So it will be necessary kind of to perform some treatment to them, plasma treatment or chemical treatment to improve the adhesion. Thank you guys for listening.
Thank you very much.
Thank you.
Actually,